Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lecture, we studied modal analysis of multi-degree of freedom systems with structural damping, and we covered proportional and non-proportional structural damping model. In this lecture, we are going to study modal analysis of multi-degree of freedom systems with viscous damping, and we are going to focus our attention on proportional viscous damping model. So, in practice, wherever viscous damping forces are there or the viscous forces are there which are responsible for dissipation of energy, then we can model such systems through a multi-degree of freedom viscous damping model. In many other situations where viscous forces may not be predominant sources of dissipation and other kind of mechanisms might be present for energy dissipation, in those situations also one may prefer to use a viscous damping model to represent a system, to represent damping force in the system, because such a model offers ease in the mathematical analysis both in the time and frequency domain, and hence multi-degree of freedom models with viscous damping are widely used. So, the brief outline of the lecture today is that first we are going to derive equations of motion for a multi-degree of freedom system, taking the example of a 2-degree of freedom system. Then we will define eigenvalue problem, we will find the response, the free vibration response of the system, then we will look at the model of the system, and then we will find out the force response of the system to harmonic forces acting on the system. And then we will define frequency response function and frequency response function matrix and see their relationship with the model. So, therefore, let me formally write down the topic today is modal analysis of multi-degree of freedom systems with viscous damping, right, and we are going to look at proportional viscous damping model. So, we are going to assume that the system has damping distribution that is proportional. So, let us look at the equations of motion for a multi-degree of freedom system with viscous damping, and we are going to take the example of a 2-degree of freedom system, the system we considered while discussing multi-degree of freedom undamped systems, and then we are going to now add viscous dampers to that system and then derive the equations of motion. So, let us first quickly sketch that system first. So, we have these two masses, then we have this fixed supports here, right, and the masses can be assumed to be moving on rollers so that they can move in the longitudinal direction, and we have the spring here, a damper here, another spring and damper, right. So, let us say this is mass m1, this is m2, stiffness k1, k2, k3, damping coefficients C1, C2, C3. So, these are viscous damping coefficient, right. And now let us say that this mass m1 undergoes a displacement x1, let it has velocity x1 dot and acceleration x1 double dot. Similarly, this mass has displacement x2, velocity x2 dot and this acceleration x2 double dot. And let us try to now draw free body diagrams of both the masses under a displaced state and identify the forces which would act on these masses. So, let us say this mass m1 moves to a location which is x1 distance away from its mean position. This is m1. Similarly, let mass m2 moves to this location with its distance x2 from its mean position, like this. And now the forces which appear are k1 x1, this x opposite to x1, then we have damping force c1 x1 dot, then we have the force due to spring k2 and this would be k2 x2 minus x1, and then we have the damping force acting on the two masses and that would be c2 x2 dot minus x1 dot, and then we have the spring force due to k3, that is k3 x2, and then the damping force due to c3, which is c3 into x2 dot. So, this is how we have made the free body diagrams, right, of the two masses. And now let us apply Newton's law to write equilibrium equation for each of these two masses. So, by Newton's law, for mass m1 x1 double dot should be equal to summation of all the forces, algebraic summation of the forces acting on mass m1. So, the forces which are in the direction of acceleration should be taken as positive, forces which are opposite to the acceleration direction should be taken as negative, and hence we write down minus k1 x1, then we have minus c1 x1 dot, then we have plus k2 x2 minus x1 and plus c2 x2 dot minus x1 dot. Similarly, for mass m2 we have m2 x2 double dot, and then we have the forces which are minus k2 x2 minus x1 minus c2 x2 dot minus x1 dot, and also again minus because k3 x2 is again opposite to x2 double dot. So, k3 x2 minus c3 x2 dot, right. So, this is how we got these equations. Now, we can shift all the terms on the right hand side to the left and we get, and also we collect all the terms with identical variables together. So, let us first of all write down the coefficient of x1, that is going to be k1 plus k2, then we have the coefficient of x2, that is minus k2, then we have the coefficient of x1 dot, that is c1 plus c2, and then we have the coefficient of x2 dot, which is minus c2, this should be equal to 0. We can also do similar thing for, I think I have mistakenly written it as x2 double dot, it should be x1 double dot. So, x2 double dot m2 x2 double dot plus coefficient of x1 is minus k2, right, then coefficient of x2, that is k2 plus k3, and then we have the coefficient of x1 dot, that is minus c2, and then we have the coefficient of x2 dot, right, that is c2 plus c3, right, that is what we get. Now, we can combine these two equations in matrix form, right, by defining vectors of displacement, velocity and acceleration. So, therefore, what we get is x1 double dot, x2 double dot, which can be written as we get a mass matrix 0 m1 0 0 m2, then we have the damping terms, velocity vector which is x1 dot x2 dot, and the terms are c1 plus c2 minus c2 minus c2 c2 plus c3, and then we have the displacement vector x1 and x2, and the terms in the matrix are k1 plus k2 minus k2 minus k2 and k2 plus k3, right, and this is equal to 0 0. So, therefore, this is the matrix form of the equation, and then we can represent symbolically this equation as the matrix. We can represent it as mass matrix multiplied by acceleration vector plus damping matrix multiplied by velocity vector x dot, then we have the stiffness matrix multiplied by the displacement vector, and it should be equal to 0. So, right now we are considering the free vibration of the system, and hence on the right hand side the vector is 0. So, this is nothing but the equation of motion of the system. So, this is the equation of motion, and we have now got a mass matrix, stiffness matrix and damping matrix representing the system. So, these matrices M, C, K, which are the mass damping and stiffness matrices, they now make the spatial model of the system. So, this system with viscous damping is represented by mass, damping and stiffness matrices, okay, and we note that they are symmetric because of the principle of reciprocity, right, and currently they are of order 2 by 2 because we have considered a 2DOF system, right. Of course, for an NDOF system, we will have mass, damping and stiffness matrices of order n by n, right. So, you can see this is how basically we obtain the equation of motion for a system, multi-drop film system with viscous damping. Now, we are going to use a proportional viscous damping model for the further analysis, right, proportional viscous damping. So, when the damping distribution can be considered or is a combination of linear combination of mass and stiffness matrix, or is proportional to either the mass matrix or stiffness matrix, it is called a proportional damping model. There exists also a more general definition of proportional damping, right, but let us use this particular model because it is widely used for modeling the proportional damping in the system. So, let C is equal to nu K, that is the proportionality coefficient, into K plus nu M, that is M, mass matrix, okay. So, C is therefore is a linear combination of the mass stiffness matrix and mass matrix, and nu K and nu M are proportionality constants, damping proportionality constants. So, these constants basically define that how damping matrix is related to mass and stiffness matrix. So, if these constants are given, the damping distribution gets defined, right. Let us now try to define the eigenvalue problem for the system, okay. So, let us go to next page, and now we are going to define, because we would like to then find out what are the eigenvalues and eigenvectors of this system. So, let the displacement be given by x naught e to the power st, right. So, let us say this is the displacement, and because of damping the response is going to decay. So, that is why we have taken s in the exponent of exponential, right, in the power of exponential, because s is a complex number here. That would help us to model the decay of vibration. So, substituting this in the equation of motion, what we get? We get m s square x naught plus s c x naught plus k x naught into bracket e to the power st is equal to 0, right. And we can also therefore, in this case for an arbitrary t, e to the power st cannot be 0 for an arbitrary t, and hence the only way this equation would be satisfied is when s square m plus s c plus k x naught is equal to 0. When this is satisfied, this particular equation is satisfied, then only the solution that we assume can be the solution of free vibration of the multi-diaphragm system with damping. So, this basically represents an eigenvalue problem, right. This is in the form of a eigenvalue problem and represents a quadratic eigenvalue problem. It represents a quadratic eigenvalue problem. So, in the undamped case, if we recall, we did not have the term like dependent which is related to the damping, because there was no damping in the system, and therefore, we could then find out the eigenvalue problem was something like a linear eigenvalue problem in terms of lambda, right. But here now we have not only the s square term, we also have the s term along with the constant k term, and hence it becomes a quadratic eigenvalue problem. So, this problem is more challenging to solve than the linear eigenvalue problem, but for the present system we are dealing with, a system with proportional viscous damping, we can find out the eigenvalues and eigenvectors of the system little more easily, right. And let us try to do that, and we will basically use a modal approach to find the eigenvalues and eigenvectors, right. So, we are going to use a modal approach. So, here what we are going to do is that we would assume that let the free vibration solution is given by phi r e to the power s r t, right, where s r is the unknown eigenvalue, right. Eigenvalue of the system, and then we have phi r, which we are taking as the rth eigenvector of the corresponding undamped model of the system, right. So, it is nothing but the rth eigenvector of the corresponding undamped model of the system. And what is the corresponding undamped model? If we just consider the mass and stiffness matrix of the system, right, and ignore damping, then that model is the undamped model of the corresponding undamped model, right. And by solving that model, we can find eigenvectors, and this phi r is nothing but the rth eigenvector of that system. So, let us assume this kind of solution, right, and check whether it satisfies the equation of motion of the viscously damped system. Let us substitute this equation in the equation of motion and also pre-multiply by phi r transpose. So, if you do that, then what we get? We get SR square phi r transpose m phi r, right, and plus SR phi r transpose C phi r, right, and then we have plus phi r transpose K phi r, right, and this is equal to this is going to be equal to 0, right, because we are going to have a scalar. Phi r transpose 0 will be a 0 value, it is a scalar quantity, right. So, here if we say that, let us say phi r is nothing but a mass normalized eigenvector of the corresponding undamped model. So, in that case, if we use the orthogonality properties, then what is going to happen? This S r square phi r transpose m phi r would be simply 1, and then phi r transpose C phi r. So, in this case, what is going to happen? We can substitute the proportional damping model we have assumed, which is nu k plus nu m, and then this basically becomes nu k, right, and phi r transpose k phi r is nothing but omega r square, right, where omega is the r is the undamped rth eigen natural frequency of the corresponding undamped model, and we have nu m, and phi r transpose m phi r would be unity, hence we get this term here, and then plus phi r transpose k phi r is nothing but omega r square, and this is equal to 0. So, we can see this is the equation we obtained, right. Let us go to next page and further look at this equation. So, the equation we have obtained is S r square plus S r nu k omega r square plus nu m, right, plus omega r square. So, here we should note that this omega r is nothing but the rth natural frequency of the corresponding undamped model, right. Now, this equation something in a form which is similar to the equation characteristic equation we get for a single degree of freedom system, right. So, for a single degree of freedom system with viscous damping, the characteristic equation we had was ms square plus cs plus k is equal to 0, and if you divide by m, this equation becomes c by m s plus k by m is equal to 0. And we have seen in the case of single degree of freedom system, the lecture, that we can write this as s square to zeta omega n s plus omega n square. So, this is nothing but the characteristic equation for a single degree of freedom system and with damping factor zeta. So, if you compare the equation we got with this equation, then we can say that we can rewrite this equation in this form: 2 zeta r omega r s r plus omega r square, right, where zeta r is nothing but the the modal viscous damping factor of the rth mode is the rth modal viscous damping factor. That is what it must be representing, because when we compare these two equations, the one we got for the present case and the one with the we had got for the single degree of freedom system, then zeta for single degree of freedom system represents damping, and the equation we have got, therefore, it is in similar form, and hence zeta r must also represent damping of the system. Therefore, the solution we assume, right, that satisfies the equation of motion of the viscously damped multi-degree of freedom system, and hence the undamped modal eigenvector also forms the eigenvector of the viscously damped system, right. And then what are the eigenvalues? Eigenvalues can be obtained by solving the equation just now we got, right. If we solve this equation, so this equation has got two roots, so let us call them as if I call them by SR1 and SR2, then this would be minus 2 zeta r omega r plus minus, and that is 2 zeta r omega r square minus 4 omega r square upon 2, that is nothing but the roots of the quadratic equation, and which can be then simplified as minus zeta r omega r, maybe I can take omega r common, then I get minus zeta r plus minus square root of zeta r square minus 1, right, into omega r, right. And if I assume that let system be underdamped, let the system be underdamped, which means the damping factors or damping the system is less than the critical value. So, in that case the zeta r would be less than 1, and hence these roots can be written as r1 r2 is equal to minus zeta r plus minus I, the roots should be complex conjugate, and we get zeta r square omega r. So, these are nothing but the roots, these are nothing but the eigenvalues of the viscously damped system, right. So, therefore, here the omega r represents the natural frequency of the mode, which is now same as the natural frequency of the undamped system, and zeta r represents the viscous damping factor of the rth mode. Right. Let us go to the next page. So, therefore, we see that the solution we assume x is equal to phi r e to the power SRT, that indeed satisfies the free vibration equation, and hence the phi r and SR together form the eigenvalue and eigenvector of the rth mode of the multi-degree of freedom system with proportional viscous damping. So, therefore, we can define the now modal model, right. So, one way to define the modal model could be that we have now eigenvalues, complex conjugate eigenvalues, right, which are given by SR1 SR2 is equal to minus zeta r omega r plus minus I under root of 1 minus zeta r square omega r, right, where omega r are the natural frequencies of the undamped model and zeta r can be obtained from the knowledge of the proportionality constants and the omega r, and that is nothing but equal to we know that 2 zeta r omega r, right, that is equal to nu k omega r square plus nu m, right. So, from this equation we get zeta r as nu k omega r upon 2 plus nu m upon 2 omega r. So, this basically gives us the damping factor. So, once we have the knowledge of the proportional damping constants and natural frequency of the undamped model, the damping factor of the damped model or the damped system can be determined. So, these therefore complex conjugate eigenvalues are there, and then these are defined for r is equal to 1, 2 up to n if it is an integer freedom system. And then we have the eigenvectors, right. These eigenvectors are the eigenvectors of the corresponding undamped model. So, the same eigenvectors also define or make up the eigenvector of the damped system, the system with proportional viscous damping. And because the undamped eigenvectors are real, the eigenvectors of the multi-degree of freedom system with proportional viscous damping are also real, right. They are real eigenvectors. Okay. So, this is how we can define the model of the system. We can also prescribe the model, so that we can call as method 1, and alternative form in which the model can be prescribed is we simply provide the natural frequencies of the undamped system, the damping factor zeta r calculated from the formula above, and the eigenvectors of the undamped system for with r varying from 1 to n. So, these quantities also together basically make up the model, and if these are given, the dynamic of the system gets defined, right. We can identify or determine the free vibration solution. So, what is free vibration response? If we look at, let us say, a response in RF mode, and if you use only one of the eigenvalues, right, that eigenvalue is complex, and hence the response would be complex, and it would not be able to represent a response which is real, right, for the real matrices. And hence we basically require both the complex conjugate eigenvalues, combination of the two, in order to represent the response of the system, the real response of the system in one of the modes, right. So, therefore, in RF mode, the response, free vibration response represented by, let us say, XR, can be written as A R phi R E S R T plus A R star phi R E S R star T, correct. So, here AR and AR star are complex conjugate coefficients, right, and SR and SR star are complex conjugate eigenvalues. So, star basically represents complex conjugate operation. So, the general solution, general free vibration solution would consist of a linear combination of free vibration in each of the modes. So, all the modes need to be linearly combined, and hence we can then write this as X is equal to A R phi R e to the power SRT plus A R star phi R e to the power S R star T with R varying from 1 to n. So, this is a general free vibration solution, and if you substitute the complex eigenvalues expression here, SR is equal to minus zeta R omega R plus square root of 1 minus zeta r square into omega r, and then use the Euler's identity and then simplify. We can also write this in this form, minus zeta r omega r t, and some new arbitrary constants appear, say dr into cos omega r under root of 1 minus zeta r square t plus e r sin omega r under root of 1 minus zeta r square t, with r varying from 1 to n. So, this is nothing but the general solution for the free vibration, and dr and er are arbitrary constants and can be found out from the initial conditions. So, if initial conditions are given, we can find the arbitrary constants, right, because there are now 2n number of arbitrary constants, and then we will have so n values of dr and n values of er, and then we have 2n our initial conditions like n values of displacement and n values of velocities at t is equal to 0, and then we can solve the equations, right. This will be basically an algebraic set of simultaneous equations. So, in this way we can find a free vibration response. Let us now consider the force vibration response of the system to harmonic forces. So, force vibration response to harmonic forces. So, the equation of motion basically now we will have a non-zero right hand side vector, which basically defines the force vector, and the equation of motion will be of this form, mx double dot plus cx dot plus kx is equal to f, right, f of t, right. And if you assume harmonic forces, means all the forces acting at all the degrees of freedom, right, they are at frequency omega, right. So, if you assume harmonic forces, so let us say we define the force f of t as having a amplitude f naught into e to the power I omega t, right. So, therefore, we also can assume the response to be of the same form. So, this is the steady state response. So, the total response would consist of the complementary function and a particular part. Particular part is nothing but the steady state response. So, let us first of all find the steady state response or the particular part of the solution. So, this we can assume as x naught e to the power I omega t. Because the frequency of the force is omega, the corresponding steady state response will also be at the same frequency omega, and hence we are making this assumption of the solution. If we substitute this in the equation and simplify, then we can show that x naught is nothing but equal to k minus omega square m plus I omega into c inverse of this into f naught. So, this is nothing but the amplitude of the steady state response, and this coefficient matrix we can represent, as we have also done in the case of undamped system, as alpha, and this of course is function of omega. F naught. So, here alpha of omega is the nothing but the FRF matrix and is given by k minus omega square m plus I omega c inverse. So, that is nothing but the FRF matrix. So, this is nothing but a relationship between the FRF matrix and a spatial model of the system. So, if the spatial model of the system is given, we can find the FRF matrix using this equation. So, this is nothing but a direct solution of the equations. So, let us now use an alternative approach. So, right. So, this is based on a direct solution. So, the response we got, right, this is based on a direct solution of the differential equations. As we have done for the undamped system, let us use now a modal approach or a modal analysis approach to find the response. So, in the modal analysis approach, we basically first transform the differential equations in the modal domain, right. So, we perform a modal transformation and we say that let x is equal to say phi y, where phi is the mass normalized matrix of mass normalized eigenvectors, matrix of mass normalized eigenvectors, and these eigenvectors are the eigenvectors of the corresponding undamped model, eigenvectors of the corresponding undamped model, because as we saw just now that they also form the eigenvectors of the system with proportional viscous damping. So, if you substitute this in the equation of motion and pre-multiply by phi transpose, what we get is phi transpose m phi y double dot plus phi transpose c phi y dot plus phi transpose k phi y is equal to phi transpose. Now, we have the force vector, that is F, right. And now, you are using orthogonality properties, because the eigenvector matrix is based on mass normalized eigenvectors, phi transpose m phi is a unity matrix, right. So, we get unity matrix y transpose plus. Now, phi transpose c phi can be written as a diagonal matrix of with diagonal terms 2 zeta r omega r, right, because we saw in the previous case that each of the equation in the modal domain, right, in the case of free vibration, we got basically 2 zeta r omega r term, right, when we compared the equation we got with the corresponding with a single degree of freedom system with viscous damping, right. So, this we can write as 2 zeta r omega r and then y dot vector plus. Now, phi transpose k phi would be nothing but the matrix of eigenvalues of the corresponding undamped model, that is a diagonal matrix with omega r square at the diagonal and y, and then phi transpose f will be nothing but the matrix of modal vector of modal forces. So, let us call it Fr, right. So, now these equations now are decoupled, because here all the coefficient matrices, they are diagonal, right. The unity matrix, the coefficient matrix of y dot and coefficient matrix of y, they are diagonal, and hence the equations are decoupled, and they represent basically now the equilibrium of the system in n modes of the systems, right, and each of the equation is independent and we can solve each of the equation independently. Okay. So, here therefore, if we look at the Rth equation, right, that Rth equation can be written as y r double dot plus 2 zeta r omega r y dot y r dot plus omega r square y r is equal to Fr, correct. And because the forces that are acting on the system are harmonic at frequency omega, the modal force Fr would also be harmonic, right. So, if I look at Fr, the modal force Fr, that is nothing but the dot product of the rth eigenvector and a vector of external forces, right. And this is nothing but phi r transpose, F is nothing but F naught e to the power I omega t. So, this essentially I can write as vector, it is a scalar FRO being the amplitude of the modal force FRO e to the power I omega t, is not it. So, if that is so, the modal response also can be will also be harmonic, and we can write that as YRO e to the power I omega t. Okay. So, if we substitute these two expressions in the rth modal equation, right, then what we get? We get minus omega square, right, minus omega square plus 2 zeta r omega r into I omega, right, plus omega r square into y r o is equal to f r o. That is what we get, and hence the modal response amplitude is given by f r o upon omega r square minus omega square plus I 2 zeta omega omega r. That is what we get as the modal response. So, therefore, if we now write down in place of FRO, we can write down phi r transpose F naught upon omega r square minus omega square plus I 2, I think I should have r here, 2 zeta r omega omega r. So, this is nothing but the now modal response amplitude in rth mode, right. When the force vector is given, amplitude of the force vector is given, and a model is there, we can find now the modal response from here. So, now we can find the physical response. So, let me write here, this is nothing but the modal response amplitude, right. I can also say rth modal response amplitude, rth mode modal response amplitude, right. Let us now determine the response in physical space or physical coordinates. So, physical coordinates, response in physical coordinates, and that is given by x, phi, y, right, and that we can write as summation of phi r y r over r varying from 1 to n. So, now we substitute y r here, right, and that would be phi r. Now, y r is nothing but y r o e to the power I omega t, right. So, if we substitute now y r o we got on the previous page, then we get phi r transpose, right, divided by omega r square minus omega square plus 2 plus I 2 zeta r omega omega r, right, and then we can write down the vector f naught outside this, and we have I omega t, because f naught is basically constant vector for this summation, correct. So, this is nothing but this, and if you compare with the solution we assumed x naught e to the power I omega t, then this quantity is nothing but the amplitude of the steady state response vector, right, and therefore, we can write this as x naught is equal to phi r, sorry, I am sorry, I have missed a subscript r here. So, phi r into so we can write this as phi r transpose divided by omega r square minus omega square plus I to zeta r omega r with r ranging from 1 to n multiplied by f naught. So, this is nothing but the amplitude of the steady state response due to harmonic forces. So, what we note, we can, if you see the term in the bracket, now this amplitude, this response is complex, correct, because we have a complex number in the denominator, and which basically indicates that the response is not in phase with the force, it is having some phase angle with the force. So, this response is going to in fact lag from the with respect to the force that is being acting, and but this phase angle is same for all the degrees of freedom. So, all the degrees of freedom, they do have a phase with the force, but they have a same phase, which means all of them have a synchronous motion, right. And this can be understood from the from the fact that if we represent the denominator through a polar in the polar form, then we will have a common phase angle for all the degrees of freedom. Let us write down on the next page. So, if you represent the steady state response like this, then we have phi r transpose divided by, now we can represent it in polar form. So, magnitude would be omega r square minus omega square plus 2 zeta r omega r square, right, into e to the power say I theta. So, that is the polar form of the denominator multiplied by f naught. So, therefore, this can be written as phi r transpose omega r square minus omega square plus 2 zeta r omega r square and now this quantity is in the numerator. So, e r to the power minus I theta. So, we can see that there is a phase lag, of theta, there is a phase lag of theta. So, theta is the phase lag, and this is given by tan inverse 2 zeta r omega r divided by omega r square minus omega square, right. So, that is nothing but a phase lag. So, what is the total solution, right? This we got the steady state response. So, we can write the complete or total response as sum of the complementary part. So, let me write use the xt to represent total response. So, xt is equal to the complementary part of the response plus the particular part of the response, which is x, right. So, the total response in the time domain will be the complementary part of the response we wrote earlier, the free vibration response, which we can write as say let us use index I or maybe index j. So, a j or rather let us write in the trigonometric form we got later, e to the power minus zeta j omega j t into bracket dj cos omega j under root of 1 minus zeta j square t plus e j sin omega j under root of 1 minus zeta j square t, right, with j varying from 1 to n plus. So, that is the complementary part, and then we have a particular part which is nothing but the now we need to take the real part of this, right, because the forcing function we initially took f naught e to the power I omega t. So, we have to take real part of it. So, therefore, we can write down the response, the particular part of the response as phi r transpose divided by omega r square minus omega square plus 2 zeta r omega r square, right, multiplied by f naught vector, and then we have the real part of that. So, e to the power I omega t into e to the power I minus I theta will be e to the power I omega t minus theta, and real part of that will be cos omega t minus theta. So, we have f naught and then we have cos omega t minus theta, right. So, that becomes the basically the total response. Let us now define the frequency response functions. Right. So, let us say we want to find out what is the frequency response function alpha j k. So, frequency response function is based on the steady state part of the response, right. So, let us write down the equation for the steady state part of the response. Again we got in terms of the modal characteristics, and that is nothing but phi r transpose divided by omega r square minus omega square plus I 2 zeta r omega r, that is what we got, right, into of course multiplied by f naught. So, that is the amplitude of the steady state part of the response, and therefore, if you want to find out alpha j k, which means the response at j degree of freedom when a unit harmonic force is applied at the k degree of freedom with no force applied at the other degrees of freedom, remaining degrees of freedom, then for such a for such a situation the amplitude vector of the forces would be simply a vector with all zeros except unit force at the kth degree of freedom. So, this is the kth df. So, this is the force vector. So, if you substitute this force vector in the equation above and simplify, then what is going to happen is we will be left with only the jth or the kth element of the this eigenvector. So, we will have k r here, and then we will have omega square plus I 2 zeta r omega r, right. And since we are interested in the response at j degree of freedom, that response can be extracted from here, which we can call as xoj, and that can be simply written as phi. So, the jth element of the this eigenvector needs to be picked up. So, phi j r phi k r upon omega r square minus omega square plus I 2 zeta r omega r, and this is supposed to be the response of the force at the kth degree of freedom, right, with unit amplitude, and hence this also must be the frequency response function alpha j k, right. So, you can see the FRF alpha j k is in the form of now a series is consists of sum of n number of terms, each term corresponding to one mode of vibration, right. And we also note that the FRF here you can see it is complex, it is no longer real as we got in the undamped case. It is a complex FRF, which means it has magnitude and phase, that is it has magnitude and phase both. That is what the complexity of the FRF indicates. We can also obtain the FRF matrix, right. If you look at the above equation, then the and if you compare it with the equation we got through direct solution, which was in the form of vector x naught is equal to matrix alpha into vector f naught. So, if you compare this coefficient term here is nothing but the FRF matrix, and hence we can simply write down the FRF matrix as phi r transpose upon omega r square minus omega square plus I to zeta r omega with I varying from 1 to n. So, this is nothing but the FRF matrix. We can also write this in the matrix form, the right hand side, and we can if you put the all eigenvectors in matrix form, this is going to be something like this. So, we have the diagonal matrix of omega r square minus omega square plus I to zeta r omega, right, a diagonal matrix, and we have phi transpose. So, this is a compact representation of the equation which is in the form of a summation function. So, this is how I think we have got the FRF matrix. So, I think we can stop here, and then we will continue our discussion on the multi-degree of freedom systems with viscous damping in the next class. Thank you.